And so let me see if I can use this tool to draw a circle. Right. So that's the cross section. And although in my original picture my coordinate system showed different directions for x and y, if we rotate this picture around, we can get an x going in this direction and a y going this direction, which is kind of the more usual way to kind of look at that. And we're going to look at the position of a typical point P. So here's some point P that starts out at coordinates x and y. And as a torque is applied to this, that's going to rotate to be some new point P star, and its final locations we'll call x star and y star. Now with reference to the center of the shaft, we have these 2 points being equal, and it travels along an arc that goes through there, connects those 2 points. And we'll put some additional information on here. We can say that the distance to that point is the radial distance r, and we'll call the initial angle of position phi, and the angle of rotation we call that theta. So we'll look at that again as well. We'll call that the origin O. If we look at the small triangle with the phi angle in it, then this distance would be r sine phi, and this one would be r cosine phi. That would be our y, and that would be our x position. So if we want to look at the displacements of the points, the displacement in the x direction is equal to the x position, the final, minus the initial, and the displacement in the y direction, the v displacement, would be the initial, the final y position minus the initial y position. And by the same reasoning as what I have in this picture, the u displacement then will be equal to r, stays constant, cosine theta plus phi minus cosine phi, and the v is going to be equal to r sine theta plus phi minus sine phi. By those trig identities, I can rewrite this. So r cosine theta cosine phi minus sine theta sine phi minus cosine phi. And for the v, r sine theta cosine phi plus cosine theta sine phi minus sine phi. Now the w displacement is 0, since the bar we've assumed is inextensible, doesn't get longer in that direction. Now since x is equal to r cosine phi and y is equal to r sine phi, we can make that substitution in here as well. And writing these lines down again, u will be equal to x cosine theta minus y sine theta minus x, and v is equal to x sine theta plus y cosine theta minus y. And then we can factor out an x from a couple of these terms. And a y from the next terms. Now we're going to have small deformations and small rotations in this particular example. So in this case, that angle will be small. So we're going to make the approximation that the sine theta is approximately equal to theta itself in radians, and the cosine theta is going to be approximately equal to 1. And so, with that information, these two terms effectively disappear, and the sine theta turns into theta, so this turns out to be minus y theta, and this one turns into x theta. Now if we recall from our beginning of our discussion, the angle theta is equal to the twist rate times the distance down the length of the bar. So we can write this in terms of twist rate as minus beta yz and plus beta xz. Our strain displacement equations, epsilon ij is equal to 1/2 partial of ui with respect to xj plus the partial of uj with respect to xi, gives us two non-zero shearing strains, gamma yz and gamma xz. Gamma xz, the engineering shearing strain, is the partial of u with respect to z plus the partial of w with respect to x. Now since w is equal to 0, what we get is the partial of u with respect to z, which can be minus beta y. And likewise, gamma yz is equal to partial of v with respect to z plus the partial derivative of w with respect to y. Now the partial of v with respect to z is based on this term, that would be a beta x, and then w is 0, so we get no contribution there. By Hooke's law, tau is equal to g gamma, where g is the shear modulus. So tau xz is equal to minus g beta y, and tau yz is equal to g beta x. So from this we can write down our stress tensor. We have 0 stresses in these positions. We have a non-zero tau xz and a non-zero tau yz. Being symmetric, we have these stresses in these positions as well, and we have a 0 sigma z. down the axis of the bar. Let's take a look at our boundary conditions. And for that, I'm going to use the circle tool. Here's the center of our bar. We need to find the components of a unit normal that points in that direction. Now the unit normal would ordinarily have components like N1, N2, and N3. And we might even call them L, M, and N in this case. The boundary conditions, the tractions, would be the T sub I, and we know that the traction vector components, T sub I, can be determined from the stress tensor sigma ij nj. So if we wanted to draw these out in a matrix format, we have the three components T1, T2, and T3 equal to the stress tensor times our unit normal components. Now this being the x direction and the y direction, and the angle we can call phi off to that unit normal, not drawing a very straight line there. But we can find this dimension to be the radius of the shaft, the diameter being 2a, the radius would be a. This dimension would be a cosine phi, and this dimension would be a sine phi. So we would have the components cosine phi, sine phi, and 0. Now we have a traction-free surface. Okay, so that means there are no stresses on the outside edge of the bar along the length of that bar. There are stresses internal to it, but there's nothing that is being applied to the outside surface. As long as we're away from the load application point, that will be a traction-free surface. So all those traction components have to have a net sum of 0. Well, the first two are pretty easy to see that they're going to be 0. If we take cosine phi, sine phi 0, multiplied by the first row, we get 0. Same thing for the second row. But the third component isn't quite as obvious. So here we have T3 is equal to tau xz cosine phi plus tau yz sine phi plus 0. And we want to find out, is that really equal to 0? Alright, well, cosine phi is equal to x over a. Sine phi is equal to y over a. And we have our expressions from the previous page for tau xz and for tau yz. So we've got g times minus beta y times cosine phi, which is x over a, And then here we have tau yz, which is g times beta x, times sine phi, which is y over a, and that does indeed equal to 0. So we have a traction-free surface. The next thing we want to do is we want to figure out how these stresses inside of this bar relate to the externally applied torque. And for that, we're going to draw our circle again. And since we're talking about coordinate stresses, we'll take a look at a little square out here. Some distance x over and y up that has the coordinate stresses tau xz and tau yz acting on it. If we want to do the summation of torques, we can take that way as positive. We're going to have to integrate over the area the positive contributions, the tau yz times the x distance, and counteracting that is the tau xz times the y distance. We have to integrate that over the area, so we have units of torque, and that would be equal to the resultant torque. Now we have our expressions for tau yz and tau xz. They both have g and beta in them, and those are constants. For a bar with a constant applied torque at the end, the twist rate is constant, and the material properties are constant. So g and beta can come out in front, and we're left with an area integral of x squared plus y squared dA. We can convert that into a polar coordinate type variable, so we have an r squared dA. And this r squared dA is only a function of the cross-sectional properties. And this is known as the polar moment of inertia. I'm going to use the symbol I sub p. So what do we have here? We have the torque is equal to g beta times the polar moment of inertia. All right, let's take a look at equilibrium and compatibility. The stresses are first order in X. The only one that we really have to take a close look at for equilibrium, again, we're neglecting body forces, would be the equation that looks like the partial of tau xz with respect to x plus the partial of tau yz with respect to y plus the partial of sigma z with respect to z equal to 0. Well, partial of tau xz, let's go ahead and write those down so we have them handy. I think I wrote them on a previous page. Tau xz is equal to g times minus beta y, and tau yz is equal to g times beta x. So the partial of tau xz with respect to x is equal to 0. The partial of tau yz with respect to y is equal to 0. And then we don't have any sigma z, so that does indeed satisfy equilibrium. Compatibility is satisfied because these are at most first order in x and y. The strains will be first order in x and y. Compatibility equations include strains that are second partial derivatives of spatial coordinates. So compatibility is also satisfied. Let's make a little bit of room. And the last thing we'll look at, one of the last things we'll look at is the traction vector for the stresses that are inside of this material. So if we were to look at any particular stress state like this, the traction inside the material would be a vector that looks like tau x z in the e hat 1 direction plus tau y z in the e hat 2 direction plus 0 stress in the 3 direction. We have our substitutions that we've made for these in terms of the twist rate minus beta yg and plus beta xg. We can find the magnitude of this traction vector. It's the square root of t dot t. We can have a square root of beta squared g squared x squared plus y squared, which we can call that r squared again. When we take the square root, we'll end up with beta gr. Again, this is a constant. That's a constant. And this is the distance from the center of the bar. So, if we wanted to plot a stress distribution, what that stress distribution would look like would be something that increases as R increases. It becomes a maximum on the outside of the bar. So this is our typical undergraduate mechanics materials shear stress distribution. Now if we recall that the torque we found was G times the twist rate times the polar moment of inertia, from this the G and the beta is equal to T over the polar moment of inertia. Then the magnitude of the tractions inside the material is equal to torque times R. So G beta is equal to T over I sub P. Magnitude of the traction vector is equal to TR divided by I sub P. And if we wanted the maximum shearing stress, tau max, then that would be equal to the torque times the radial dimension A. This is the position R is equal to A. T times A divided by I sub P. And typically the way I write it in undergraduate mechanics materials is torque times the diameter over 2 divided by the polar moment of inertia. So again, this is another example of using the semi-inverse method. Some people may call it the St. Venant semi-inverse method. This is another example of just using that method to assume a certain displacement field, or we've done other examples where we looked at stress fields that would go to strain fields, integrating our strain displacement equations to get displacement components, or seeing how that works out, and coming up with some idea of how this bar stress distribution or displacement fields or strain distributions take a look at after these particular fields are applied. And we've also gone through the process of checking equilibrium and compatibility. Those two features make sure that we have a unique solution to this problem, make sure that our fields do not overlap on one another, that 2 points do not split apart, or 2 points do not come together to be 1 point, and 1 point does not split apart to be 2 points. So we have our continuum assumptions that we're using in our elasticity class.